Let's talk about work. Now, you learned in trig that if the force F is constant, the work done is defined by the product of the force and the distance that an object moves. So work is force times distance. And a couple of reminders for units. A newton is the force required to give a 1 kilogram mass an acceleration of 1 meter per second squared. That's named after Sir Isaac. And a joule is 1 newton meter. So this is the work done by a 1 newton force over a distance of 1 meter, and that is named after James Prescott Joule. Now when we look at this work, then we say it is the force times the distance, and that's great, but this is only true if the force is constant. So what we're going to now consider is, what if we have a variable force applied, and we're going to go ahead and apply this variable force. Whoops, try and make that a little straighter. We're going to be looking on this interval from A to B, and when we apply this variable force, how are we going to do this? Well, probably used to this by now. What if we divide this up into some intervals, and we'll call our little widths of our intervals delta x, and over that delta x we'll pick some representative x bar sub k, and we'll see what the force is there, and we can multiply the force times the distance on that interval, and I'm sure you can see where we're going with this. Then we could sum up these intervals and we could get an approximate for the work. We'd sum up these n intervals and we'd have the force on that representative x bar sub k in the kth interval, multiply it by our little distance for that interval, which would be delta x, and then we would let the number approach infinity, and of course then our delta x is going to approach 0, and we have our integral. The work done by a variable force F in moving an object along a line from x equal a to x equal b in the direction of the force is the integral from a to b of this f of x dx. So following this video is going to talk about the conceptual development of work, and there'll be several examples of different types where we can see this applied. We may be given some variable force function, and then we can go ahead and put that in here, compute this integral, and have the work. Now there's going to be a few other types of work computed based on different scenarios and forces. So the first one of these we're going to look at is if we have a spring and mass system. So we have this equilibrium position where the spring is neither stretched nor compressed. Then you could compress the spring, and the spring's going to want to push the mass back. You could stretch the spring, and the spring is going to want to pull back to equilibrium. Hooke's law says the force required to keep the spring in the stretched or compressed position x units from the equilibrium is given by kx. So you can see if I have the spring stretched, if I graph this function, the spring stretched, I would have this positive force because I'd have to apply this force in the positive direction to stretch the spring. And then if I needed to compress the spring, I'd apply this force in the negative x direction. And so I have this negative sign on the force. Now, if we're looking at this, then we can just go ahead and take our work integral, and for the force we can put in kx. So the work done to stretch or compress a spring, integral from a to b of f of x dx. In the case of the spring mass, that f of x is going to be kx, and then we could compute this. Now, just a caution, something to be careful. Typically, math books and these calculus books are going to define this as we did, that the force required to stretch the spring or the force required to compress the spring. However, some physics and engineering books define it a little bit differently, and they may look at the perspective of the force exerted on a mass by the spring. So rather than the external force required to stretch or compress, they're saying, what is the spring doing? And if you do that, then you essentially have this negative on this kx, because if you have the spring compressed, the force the spring's applying, it wants to get back to its equilibrium position, so it's pushing in the positive x direction. But if you have the spring stretched, it's wanting to get back to equilibrium, and so it's pushing in the negative x direction. So just be aware of that depending on how it's defined, and you'll see, because k will be a positive constant, and K is found by seeing what force it would require to stretch the spring a certain distance, and you can plug in the distance here and the force here and be able to compute that K value. And so that's going to be a positive constant, and so whether it has that negative sign on it or not is just sort of depending on how it's defined. If you're looking at what force you got to apply to the spring, or if you're looking at what force the spring applies. Typically for this calculus, it will be looking at what force to apply to the spring. There's going to be an example following this video. Now let's think about Newton's second law, because we are going to be looking at trying to compute work of something near the surface of the earth if we want to be lifting something. So Newton's second law is force equals mass times acceleration, and we know that acceleration is the second derivative of position. And the other thing that we know is if we were looking at lifting an object near the surface of the earth, then this acceleration here would be simply little g, the gravitational constant. So lifting problems, we are going to look at it's going to be force times distance, but our force is going to be mass times acceleration, acceleration being g. And then y would be our distance that we are lifting something. Now this would only work, however, if the distance that we are lifting something is constant. And so this is great, easy to compute if that's the case. However, if we were looking at lifting fluid or pumping water out of a tank, the distance is not going to be constant because water at the bottom of the tank has to be pumped a lot greater distance than water at the top of the tank. So we're going to need to take that into consideration, and in fact there's kind of three things we're going to need to think about. So first of all, that water at the different levels of the tank need to be lifted different distances, so it's going to require different amounts of work. Water in the same horizontal plane is lifted the same distance, so anything in a horizontal plane will require the same amount of work. And then the volume of water has a mass of its density times its volume. So we know that mass is just density times volume, and the density for water is 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So all those things are going to be useful to us as we go ahead and look on pumping fluid or lifting fluid then. So the volume, so let's look at a scenario where we've got this tank full of a liquid. So here is we've kind of got a parabolic looking tank, and we want to pump the liquid out to a level h here. So if we call this bottom here 0, we need to pump this up a distance h. Well, let's look at some representative slice here, and we can see that if we pump water out that is on this level of where this disc is, then that's got this much distance to pump out. But if we had a disc down here, it's got a lot further distance. So we're going to look at this, and let's go ahead and look at it kind of straight on in a two-dimensional situation, and we're going to divide up horizontally and get some little intervals for the various levels of water in the tank. We're going to look at some representative interval, and our little distance difference on this interval is going to be, well, we're going to go from 0 to b. And then it's going to be delta y, and some representative height then is going to be just a y bar sub k for this kth interval. So if we wanted to know the volume of this kth interval, we would need to take the area of this thing at y bar sub k and then multiply it by our little thickness delta y. So at any representative level there, it's going to be the area multiplied by delta y. So if we wanted to know the force on any representative kth layer, remember our force is mass times acceleration, and we have volume. And so to get to mass from volume, we need to take this volume and we need to multiply it by the density, and then we would need to multiply that by the acceleration, which, since this is near the surface of the earth, that's going to be g. So the force on any representative kth layer is going to be, here is our volume multiplied by our density, that gives us our mass, and then times acceleration. And now we're ready to look at the work performed by just the stuff in this representative kth layer. Now, in order to get work, that's going to be force times distance. So we've got force right here, but our distance, we need to figure that out. So in looking at the picture here, we see that that y bar sub k level needs to be raised up to h. So the distance that it actually has to be raised is right in here. And so that's going to be our h total y value subtracting off the y bar sub k, and that would leave us this difference here, and that's how far this layer would need to be lifted. And then you can see we could do that for each representative y bar sub k. H minus that would leave us the distance left. So the work is going to be this force multiplied by this distance. And now, of course, we're going to take all of the different layers and we're going to add those all up in layers, and then we're going to let the number of layers approach infinity, and the limit as n approaches infinity of this then would give us the integral. So we're going to integrate from 0 to b, and here we have basically it's our force multiplied by our distance. So just as a summary, if we have lifting problems, we can put an axis on in the vertical direction and put the origin somewhere conveniently. It made sense here to have it at the bottom of our tank. And then A to B is the vertical extent of the fluid. In our case, then we had 0 to B. And then we look at a cross-sectional area, horizontal slice, and look at the distance there and figure out how to express that distance. And then we've got that work. If it's water and other fluids, we could have a different density here. But essentially we would have that mass, which is our A sub y rho dy, multiplied by our acceleration. That would leave us our force, and then multiplied by our distance here. Now there are examples for each of these types of work following this video.